Hello, everyone. Thanks so much for being here. It's great to see people. When you book a meetup, you just put your hopes and dreams out into the world. You see all these registration comes in, and then you just hope people show up. So I'm going to say thank you to the warm weather. I think that helps. But also thank you to all of you for coming out, because this is the first meetup we're having for LLM-d, which is an open source distributed inferencing stack. You're going to learn a lot about it today from the core contributors. My name's Pete Cheslock. I am the community architect. I help build out this community, help run these meetups, and just really try to help make it a really warm and welcoming environment. If you join any of the community calls, you probably hear my voice and see my face on it. I usually wear a baseball cap, so you get full hair Pete today. We've got a great agenda here. Talks from IBM Research, from AMD, Red Hat, IBM Research, and this is what it basically looks like here. So Carlos will be kicking us off here real shortly, and then we'll be continuing on through. I think there might be some coffee, warm drinks showing up soon, right behind us. I'm going to check into that. But once we finish up, there'll be a Q&A. Doesn't mean we can't do Q&A during the talk. There's a microphone here for Q&A. We are recording this. It's through a Google Meet. So the microphone is helpful if you do have questions. But then we'll have a broader Q&A at the end. So if you do have some questions you want to talk about for any of the speakers, we'll make some time at the end for that. And then 7 o'clock, we've got some pizza, we've got some drinks, and we'll do some networking, and we'll just chat some more. So, and then event ends at 8:30. It's more like 8 o'clock. I'm probably going to start, pushing you out the doors. But 8:30 is really when we're trying to close the doors. So that's really all I have for me. I'm not going to stand between you and some of these awesome talks. So let's kick it off. A big round of applause for Carlos.
Very good. Everyone. All right, first meetup. You guys are pioneers, so thanks for coming. Hopefully this is the first of many to come. Very happy to be here. I'm Carlos Costa from IBM Research. Myself and many others are behind this project that we're so excited about. You're going to hear a lot about the core foundation, why LLM-d, right? We try to do some level setting. I know that you're all very familiar with many of the challenges here, but I'll go through step by step. And then I'll do first overview, and then we'll really deep dive on some of the features, okay? So let's talk about the elephant in the room. I mean, LLM inference is really changing how you run workloads, right? It's not your traditional cloud workload. There are many, many new challenges. So if you're in this room, you're probably familiar with the challenge of scaling AI, okay? Whether you're running small models that fit on a GPU, or if you're running big models that need more than one GPU, maybe across GPUs, if these are MOE models, or if you have a combination of this, you're probably familiar with things like, hey, but requests don't look like traditional web requests, meaning that they vary in size. It's very hard to predict, right? Context length, batch size, all of these have tremendous impact on the compute that you need, memory footprint, right? What the hardware you use. In that sense, traditional load balances won't work, right? You need something better. SLO is the game here, okay? So do I need more GPUs? How I keep my latency down, right, while blowing my budget? So bad decisions for scheduling in inference, they have a very big price, right? And you typically charge your clients on SLO. So it's a different game. And then, of course, there are heterogeneous hardware here, right? They're great stuff, so one big player, but there are options, right? And many times, as operators, we need to exercise those options. And the other piece is, of course, now we have to deal with state, right? Back in the old web days, things are stateless. You don't have to worry about this. It happens that inference, you build your KV cache, which we'll talk a lot about tonight, which adds complexity. Now you have to manage a KV state, which I'm also talking about, and making decisions about routing, scheduling when there is state. It's complicated, right? Again, bad decisions lead to a completely inefficient environment. And then you get to orchestration, right? Inference gets very interesting because today inference is not a monolith. There are two parts, prefill the code, which we're also talking about, and then it becomes a very interesting orchestration game with a lot of knobs to optimize. And that's the reality we're living in now, right? So what I'll build here is the case. I'll double click on some of these challenges, why you're seeing this, and how this led to a bunch of the industry players coming together to create a common platform to go after this, right? And all the, fast progress in the journey that you can coming through with LLM-d, Okay, so if you bear with me, let's talk about KV management, right? This is the big one. Okay, so if you look at some of these new patterns, right? Conversational AI, agentic workflows, you see a very long prefix, right? And this is probably not news for you guys, but what is news is that reusing prefix is how you make things cost efficient, okay? When I say this, I'm talking about scaling, right? So I'm talking about like the traditional environment where you're running, of course, multiple replicas of a model. You have to make decisions about where we place a request. So things like prefix-aware routing, it's absolutely key. One of the main reasons is what I show here, okay? So remembering like a prefill when you're building your attention keys, right? It's mostly compute bound, and then decode when you're generating the tokens, auto-generative, memory bound. Those are very different, of course, phases. What you want to do is avoiding doing the prefill again, right? Because of this, recomputing, doing the prefill is tremendously more expensive, one order of magnitude at least, than just reusing a KV cache from memory. So the game in inference is how I'm in the bottom part of this graph, okay? How am I finding ways to, when I'm doing inference, finding where I cache to KV and then reuse. I know that I'm jumping very quickly to KV cache. There'll be some education KV cache for those not familiar. I'm pretty sure many of you are familiar with these problems. I just want to build the kind of notion of why this is so important. What are like the costs if you are not doing this type of optimization well? And takeaway from this slide is you want to build a system where you can track where you caching KV and route is casually based on that, right? And tremendous, again, optimizations depend on this. You hear a lot about what I'm saying here in the next sections and mine as well. The other one is what I mentioned, right? There is also the problem of pipeline imbalance. You have these very different phases in inference. And the good news is that prefill decode disaggregation, when you separate this, is something that was an exploratory topic last year, is very much reality today, right? You see a bunch of like blogs that I capture, this being used in production, prefill decode disaggregation. Matter to Mistral, who's a partner, working with us. There's still a problem here though, right? Now you have to orchestrate prefill decode instances. How many prefillers I should use? How many decoders? Parallelism level, right? It's a lot of knobs. So as an industry, one of the open challenges here is, again, is how I come up with the APIs to do orchestration of prefill decode, right? I think the value of disaggregated P&D is proven. 2026 game is how I operationalize this, how I make it simple to operate. That's the game, and you see how this is a shared challenge in the industry and how LLM is going after this challenge, making good progress. P&D creates a communication problem, but when you go to MOE models, this gets even more interesting, right? So remember, like large models, dense models where you activate everything, very complicated communication patterns, all to all. But then MOE, the ones that are really where all the attention is today, even though you're activating like it's a sparse matrix now, right? But you're still doing a lot of the all-to-all collectives. Now locality matters a lot. You want the things like close together for your expert. And also creates a problem of how you schedule, using Kubernetes, for example, how you create pods that have a notion of locality, because now they're not just independent inference engines, they actually work as a group, right? The main problem with this type of approach, this is very typical, like in HPC systems, right? Where communication, like you're optimizing for that. The problem is how you operate this on a more cloud-native environment, right? Where you're running Kubernetes, where topology and locality is not something that you get for free, for example. What are the APIs? What are the new constructs that help you to operate something like this, right? Again, I'm moving very fast, cutting to the chase, like what are the big problems? Because I want to tell that this is really something that a lot of people share in the industry, some of these challenges. And we came together, like there are a lot of knobs here. So last year, we launched our llm-d project. as an attempt to, again, bring a lot of the energy in the industry around these pain points. We launched in May last year. It's hard to believe, but this was like just 9 months ago. So the fact that you're here having this first meetup in 9 months, I think it speaks a lot about the shared pain point. But what is LLM-d? Okay, LLM-d is a full stack to scale inference, distributed inference, meaning that you're orchestrating multiple inference engines. We start with the VLLM mostly, and we're trying to do here is really make distributed inference a first-class cloud-native workload. Okay, why I say this? Before LLM-d, there are a lot of there are still a lot of very interesting projects to simplify or to scale inference. With LLM-d, we took the approach of not reinventing the wheel. Okay, there are many things that we knew it worked really well in the cloud environment. We already had load balancers, for example, in Kubernetes, gateway API, how you treat requests, all those great things that are proven, that we know it works in production at scale today. So instead of starting from scratch, we decided to build very close to Kubernetes, okay? To extend some of these things, to leverage some of the building blocks, things like the gateway API extension, Kubernetes, a new API that allows you to treat requests with a little bit more information. So you can, for example, look at metrics related to inference and make routing decisions based on that, right? And as an example of not reinventing the wheel. So if you look at this picture, there are 3 big parts that we started with LLM-d, okay? First one is the inference scheduler at the top. So inference scheduler, again, adds a mechanism to route inference requests based on metrics like KV locality, load, and any others, right? So this is actually expandable. So you can actually use what we call inference endpoint picker to build your own plugins for how you actually route an inference request in your cluster. The beauty about the inference scheduler in LLM-d is that it builds on top of inference gateway, which is an API in inference scheduler in Kubernetes. So what LLM-d is adding is, again, is the plugins specific for inference request routing. We have a few, and you hear more about them tonight, like prefill aware, KV-cache routing, load aware, and a few others, and you get like what are the benefits when you're running this. The other one, number 2 in my picture, is the support to do disaggregated serving, okay? As I said, now you have to basically manage a few variants, like prefillers, you called. You have potential like different numbers of this. Some of this is done dynamically. And the orchestration is, of course, there's like a handoff, right? You do prefill, decode, who consumes, and all of that. So operating this, you need all this orchestration, and that's a big chunk of what you see in LLM-d. Tonight, you see how we're using this approach to do prefill, decode with just a few replicas all the way to MOE models that takes many GPUs, all the way to 32 GPUs sometimes. Of course, this also involves communication, right? You have to transfer KV-cache between prefillers and decoders. Few mechanisms, you can do this point-to-point, peer-to-peer, or you can offload this and read from a storage. And here is where we also leverage a lot of the nice building blocks in the community, things like Nixo from the Dynamo stack, right? Which already established very good API to do this type of transfer. So big partner here, we're using Nixo. Also Nixo is used to connect to some of the storage providers. Also, again, leverage some of the storage providers for KV-cache, things like llm-cache, for example, being exploring now, KVBM, and also LLM-d has its own file system backend as well, right? We all unpack all of this and give you like the first, first layer. Third one is the variant autoscaler. All I said is great. When you're scaling, you need to make decisions for, again, how many replicas, whether should scale up and down based on demand and all of that, right? LLM-d, we have a autoscaler There are two modes. There is a reactive one, which is somewhat simple, which is a good thing, right? Just reacting based, again, on utilization. And we also now work on a proactive one, which is using some more like intelligence to make decisions about your PD configuration, for example, right? Very important thing is what is on the right-hand side. So if you didn't pay attention till now, I think the value proposition, like three things you should keep in mind. Make it easy to operate. Some of these stacks, they add so many new things, and I'm sure you heard many new things here. We wanted to make this very simple. Like if you operate in Kubernetes cluster, LLM-d user should be able to operate, someone coming to LLM-d should be able to operate LLM-d as well, right? So it's modular, built on standards, with very low barrier of entry if you're used to Kubernetes world, okay? Flexibility, this is by design across platform stack, meaning that it should run across different hardware providers. In fact, when we launched, this was already running on the major GPU providers and also Google TPU. And a very, very important one that I'll come back and spend some time is this philosophy of well-lived paths. What it means, as you can clearly see, there are many knobs here, and one of the hardest parts in Inference is actually deciding like how you set these knobs, right? Well-lived paths is basically like a blueprint for common patterns that you see very often in industry that we encoded in guides that can be used, is like tested, benchmarked, so you have, again, a path to deploy this in production. So this, it's really like that basically guide how I can get to value without a lot of, again, the exploration, right? And this is all coded in the well-lived paths. Important to say it again, we managed to get a lot of partners with us when we launched. You see a list, and come back to the different parts that are coming from these partners. But it's just great to see this coalition coming together because it speaks again to the challenges that you see and that we share. In these 9 months, we made tremendous progress, right? Here's some of the speeds and feeds. I'll talk to some of them now, and then I will double click through the night on specific ones. We are really, cross-vendor by design in one of the first ones, which is great. We pioneered some of the techniques that I just mentioned on Kubernetes, things like making MOE serving really viable, getting like state-of-the-art performance. You see that number, 2.2 token seconds per GPU coming back, and I think, Tyler, you expand more on that. But this is a reality with LLM-d today. Also, things like prefill decode disaggregation, again, in production with Kubernetes. You're seeing tremendous benefits, things like 3 times better latency for long prefill workloads. The idea of this state-aware scheduler, we have a dedicated section tonight on this. What are the gains? Remember my KV cache slide. What are the benefits if you start to actually optimize reuse? And like in a single word, the benefits can be this order of magnitude, 57 times faster for some workloads. And then it's still early days for autoscaler, but you already have things like scale to 0. In the case of models that are not heavily used, scale all the way down, having this done dynamically when you have SLO constraints, okay? We've seen very interesting organic pickup for LLM-d. That's when you build a community or something that is a common stack. What I want to see is, just, again, people coming to this project using, giving feedback, and helping us to build. And this is happening with LLM-d, right? We're getting GitHub stars, all those good stuff, come from like many places. But what is more important is like a community calls, people coming in, and we're starting to see more and more also engagement in terms of contributions. It's all great, but if you're operating a solution, you probably might be asking where I buy this from, right? So we also have a downstream path for LLM-d. It's part of Red Hat AI today, and some of our other partners are also looking to how this is used in offerings, okay? So a very important piece of our success is really responding very quickly to challenges as they emerge. In this room, I don't need to say that things are moving really, really fast. And new pain points, they emerge with like new models, new architectures, new hardware, right? In this picture, I try to show just how responding very quickly to emerging challenges is how we are helping to attract people to LLM-d and drive adoption. For example, last year, one of the big things was what we're calling here the prefill crunch, right? Folks understood that for long context workloads, we had a big problem, right? And how you run this on a cloud native platform. That's when LLM-d came out, making this very real prefill decode segregation in a way that you can operate. Then things evolved to the YDP models and became very, very hard to just deploy these models now taking 16 GPUs, the whole orchestration. That's when we came up with the whole support for operating YDP models. We expanded to other hardware as well. So this is running Google TPU today, all of that. And then we start to see the latency war, right? With agentic, latency became the game. More important even than throughput. And then what you see in one of our latest versions now is really state-of-the-art latency with optimizations like asynchronous scheduling, a lot of things that also I think Tyler will touch on. We're just the beginning, right? I think there are very interesting frontiers now coming up. The one that we all excited about is, of course, reinforcement learning, which is kind of blurring the lines between just inference and training. So a lot of the model customization now is through reinforcement learning. And this is, again, many times the bottleneck is actually on the inference side. So there is a very big role for distributed inference to play in this space. Things like weight synchronization, right? The synchronous execution, a lot of things. So stay tuned. There is a lot coming LLM-d for this frontier. The other one is we've been running inference as a black box type of thing, right? From a platform perspective, you're trying to predict and estimate requests. And now with agentic, you actually get to know a lot more about the workflow, right? Because this is not Carlos typing like a prompt that I have to, I don't know, guess. Now it's a agentic loop where I know an execution plan, which means I can use some of that information to drive my decisions at the platform level, right? So in LLM-d, we're looking a lot into what these workload-aware two-way communication could look like. So that's another big frontier. And finally, we're talking about AI. It's just funny how these days AI applied to systems, right? The full loop is where things get really interesting. I was talking about the scaling, all of this. So how can you apply more intelligence to how you actually tune the knobs? So a lot of the AI-driven automation, especially for the auto-scaling piece, is where there's a lot of exploration. Just to get you guys excited for what is the future, but I want to go back and talk about the today, okay? So what do you got in LLM-d today? I alluded to this already. I want to just tease you with some of the paths and the guides. I will show you a few things, and then we'll come back and look at some of the numbers. These are the paths that we have today, right? And again, just to remind, the philosophy is validated, production-ready deployment patterns. For anyone in this room today operating an inference platform, I'm pretty sure that some of these patterns will resonate. And as a call to action, please do check some of these guides because they might have a lot of the answers that you guys are looking for. Kind of quickly, I'll just skim through a few. So you see this one in detail in a little bit, but this is for scheduling. This one speaks to a lot of workloads, right? Even if you have small models, you can just make those smart decisions on where you route your request. They're very, I don't know, simple things. I say simple, but it's never simple in production. Just for example, looking at the load at the inference pods or inference instance that you have and making decisions based on that. All the way to, now let's track KV cache state. So every time you get an inference request, you build your KV. What if you emit an event that can be tracked globally, okay? And now you have the state of your whole distributed KV cache, right? What if the scheduler also know about this? And again, we can use this in metrics. That's what you see today on the prefix-aware routing. And spoiling a little bit of the thunder. These are some of the numbers that you see in details. It can be very significant when you have some of these. You see some of the workloads that you apply in this. The other one is PD. We talked about PD. I think I made the case. You're all convinced that decoupling these things makes sense. Here's the trick, though. If you do prefill decode disaggregation, it pays off in some conditions, okay? This graph is interesting. You might have seen this like a Pareto curve type of graphs, right? This shows concurrency per user output, right? And you see that, so red line is no prefill decode disaggregation, green line is prefill decode, so 4 prefillers, TP2, tensor parallel 2 decoders, tensor parallel 4, just to give an idea of like how many knobs are there. And what you see is that if you have very high concurrency, performance benefits not quite there. If you have very little concurrency, also it's not there. But if you're like in this kind of mid-range, this can be like 1.5 times better in terms of throughput, right? And this will change based on workload, model, right? So if you really want to squeeze every single last drop from GPUs, you probably want to see this like dynamically in a platform that help you to configure these things again on the fly, right? So LLM-d is helping to expose some of these, again, optimizations room for PD. You'll see more about this. Again, I'm teasing out a few things, setting the stage for the rest of the talks. YDP parallelism, this is really to say that LLM-d are using leader workset API, which is something new in Kubernetes, if you're following this, that allows us, again, to coordinate pods in Kubernetes, running VLLM as a gang, having like one leader that does like model loading on these things as a single API. So this, again, helps a lot how you actually orchestrate things. I'll let Tyler talk about this number, but you see, again, how using LWS is helping us to run like DeepSeek, again, the living state of the art. Really kind of quick through. I think the last one I'll highlight, I'm highlighting the ones that you guys hear more, is the KV cache management with CPU offloading, right? So this is when you go beyond, of course, GPU memory. We know that these models, this will happen very quickly. The slide that I showed before, I don't know if you guys saw the number, but even for a small Llama 3 7B model, one of these kind of common patterns like conversational AI, you run to like terabytes of KV cache very quickly, right? So things won't fit in memory. So you have to start, of course, looking to what are the next storage tiers. In LLM-d, you have support for CPU offloading. These are already in the release. And also now, very recent, very latest one, you also have offloads and support for a file system based storage, okay? So you can go all the way to, again, a parallel file system. There's some of the numbers here. You'll see in detail in a little bit. I'm saying all of this. One thing that we really striving in LLM-d to do is document everything, okay? It's about setting, again, blueprints and patterns that can be replicated. We keep writing these blogs for every single of these knowledge paths that I mentioned. There are details, a lot of these numbers that I show, they're all captured in blogs. And again, this is something that you feel like helps the community. And we got a lot of engagements for some of these things. So this is all great, but I started this talk talking about like a community, the fact that we can reuse some of these parts. So let me tell you where we are with that. And we're very proud actually about this because as I said, there is organic momentum. We're getting a lot of very strong feedback that it is useful. The way we run LLM-d, again, very open. They are like a community calls. Anyone, you're all invited to join. You get a sense of where the project is going, what are the things that are in the minds of all involved. You can chime in, ask, not only ask questions, but ask features or complain that things are not working. we want to hear especially the latter, right? There are 6 special interest groups in LLM-d today, very active as well, things like PD segregation, KV management, and so on. LLM-d is showing up in a lot of the conference today, which again is it's a very good validation for the interest. Very proud about this one. I know that there are some analysis folks in the room, so very happy that LLM-d is in the cluster max rating. So if you guys are familiar with SM analysis, there is Inference Max for engine performance. Can you guys hear me well? I'm sorry. Inference Max for engine performance, inference engine performance. Cluster Max is about the cloud rating. And LLM-d is used for benchmarking distributed inference. Again, very good, strong validation because Cluster Max runs on many clouds. So if you speak about being platform agnostic, hard agnostic, this is a very strong validation. The fact that some analysis folks took this and ran again across many clouds, it shows that it actually works. We're also part of CNCF Technology Radar. This one very interesting because CNCF goes and asks decision makers in this space, what are the projects that you care about? Okay, and of course, like many of the expected names will show up. LLM-d is here in like in 9 months, right? Again, it speaks to, again, this is a common pain. These are great, but what we're even more proud of is the fact that LLM-d has the upstream first philosophy, meaning that we work as a glue to many things, and we need support in different parts. So we work very close with the VLLM community. There are a lot of hooks that we help to enable there so we can use. Again, a lot of the YDP support comes from this very close relationship. And we look at Tyler because we bought Tyler and others a lot to get these things and work together. Same's happening to Kubernetes. As I mentioned, Kubernetes was not really designed for this type of workloads, which means there are a lot of things that you needed to evolve in Kubernetes. The 2 big ones is LWS, leader worker set, as I mentioned, and also the gateway API, a lot of activity in that space as well. We work very close with NVIDIA and the Dynamo community, Nixo, which is this transport layer, super close, and more recently even did some contributions to do things like transport on TCP, which is important, right? So when we're talking about communication, everybody think InfiniBand, Rocky, which translates to very expensive, right? And sometimes not accessible. So having support to networks that are, again, TCP-based is something that has spent some time. You might be looking at the thing in the left-hand side. I'm trying not to spoil something that is coming, but you get a sense. LLM-d is under application for CNCF Sandbox. Stay tuned. This is big news for the project, big step in the making. So stay tuned. But something that we're excited and looking forward to. As we get into some of the other talks, just want to give a sense of speed that we keep releasing. Please do drop in our community calls. You get a sense, again, what is going on. But if you do have a request, something that, hey, this is my pain point, this is not something that is being addressed, we want to hear. This is what is now a 06 release coming soon. Big one is RL support. And we're expanding. I think maybe I'll close with one big thing. I mentioned about being agnostic to hardware, being agnostic to platform. You also take a very important step, be agnostic to the inference engine. So today you probably saw VLM everywhere. Big important step is that LLM-d is expanding to SGLang as well. We start with basic support and we evolve from there. But if you're in this room interested, hey, I run with SGLang, is this for me as well? Please come talk to me, and I can give you an idea of what is coming. I hope I set the stage for the next talks. We'll double click on several things, but I really want and I'm very happy to invite maybe Pete, are you transferring the talk, or should I get yeah? But before I finish, please do engage. You'll see this QR code coming up all the time. We want to hear from you. Do check our GitHub blogs and the Slack. And thanks a lot for listening. Okay.
Awesome. Thank you. All right, we're going to do a quick laptop swap and hope that it goes well. We'll keep I don't know what that's important. We're going to keep some time at the end for Q&A, just to keep us going. And that way, if we're running a little late, we can just take it right into the networking section. And all the speakers will be sticking around. And you can follow up with them afterwards. All right. Oh, look at that. It just worked.
Shocking.
You
Can you hear me? Am I hot? Yeah.
All right. Welcome, Kenny from AMD.
Well, thank you. You should wait till the talk is over. That's my recommendation. I'm going to talk quickly because I wasn't quite sure who the audience was and what to say. Okay. Are there any AMD people in the room at all? There is an AMD person. Well, hello. We can talk later. Let me say that the way I got involved in this was through Rob Shaw and Tyler, who's going to speak next. And basically, they're gurus at VLLM, and they were clearing the path for PD disaggregation. And then it was brought to my attention llm-d. And so Carlos mentioned the May of last year. I wrote a blog for AMD in May of last year with PD disaggregation in llm-d. And so what we did is took Nixel and reverse engineered the library for our stack because you need that to do the KV block transfers in the back end. So this was the extent of it at the time. Since that moment in time, I fought and scrapped to get the resources needed to lift this up and push it into our planning. And I'll talk a little bit about that today. And the primary thing I want to do is to say that at AMD, a lot of what we need to do is align with our ROCm stack and align with our GPU stacks. And so those are moving targets, and we have interesting things coming. And we are doing an invested effort in this at this point. So the other thing I'll say is that aside from being a principal, I'm also a senior engineering manager in the AI team, and I manage the VLLM group in North America for AMD as well. So my team's responsible for a lot of the messes that you'll see upstream there. So let's go into this work here and see what happens. As a precursor, I can't really give you all the details. We really are pushing hard on the front of distributed inference at this point. We have disaggregation for a handful of different combinations of solutions that we're looking at. So on the left, you see disaggregation with VLLM and SGLang, as Carlos was just alluding to. We've been working on this already for months. And then the other expectations here are dealing with Mori EP versus DPP, and then in particular, carrying on combinations of those with VLLM and SGLang as the backend. Now on the right-hand side, you'll see kind of some of the planning that we've been involved in and I've been pushing into our stack and our plans. This is kind of exploratory work at this point, but what I would like to point out is LLM-d. So it's in there. We've got it. It's part of what we want to do. We at least want to test it carefully. I don't see us having a proprietary solution. However, getting our solutions posted on our ROCm documentation is a goal, and that requires some alignment with our stack. Okay, the rest of this is going to be ADER is something I'll talk a little bit about. You'll hear more about DPP and YDP integration, DBO, this batch overlapping work to be done, EP, LB, basically expert parallelism, load balancing. So load balancing is a challenging problem. And it requires you to have a scan or look ahead, if you want to think of it that way. What kind of workloads are coming in, and what can you learn about them as they're actively happening? So it's interesting. MOE, FP4 support, I'll talk very little bit about that, but we have to align with our hardware, so I have to mention it. And otherwise, you can see some of the efforts that we have going on here related to that profiling and so forth. So if I think about where we really stand, and I look at the upstream solutions that have been posted in LLM-d right now for AMD stack, There's two of the well-lit paths that were implemented. Really, I think Vincent and Tyler actually did these. I didn't publish our internal work on this, so I appreciate that very much, by the way. And so I went and tried them out. Okay, so in this concept of validated, it's kind of like, okay, what happens if we go to upstream llm-d and pull this and try to launch from the solutions that are posted there on a cluster that we have for doing some of this work. And with some doing, and I'll show you the little pain points. I'm going to expose myself as well as just talk a little bit about the fixes that we do to make that work real quickly. So those solutions are really awesome. You might take those images and try them and then bump into some issues. And when that happens, don't get discouraged. There's usually a path that you can take that will go around it. Most of you probably know better than me. But basically, YDP is going to be a work in progress for us still. I'll talk very little bit about that. PD, DSAG, we have worked on that quite a bit already, frankly. And inference scheduling, it kind of just works. And so the way to think about that is you have basically a pool of LLM servers, and then you can launch them in replicas. And then you have, as Carlos pointed out, you have scheduling going on top of those. But keeping a good line of reasoning, like correctness going for incoming streams, looking at busy state scheduling to based on metrics that get pulled from VLLM metrics by the Prometheus scraper and put into a cost function. That's kind of cool stuff. It aligns with real-time dynamic behavior of the servers on the server side, and it registers back up into the decision-making process on the routing of information. Okay, so if I just reference those, you can go into the upstream stack there, and you can see these two PRs that were merged, and these were the ones I'm referring to trying. So let's see what happens if we try it. The first thing I noticed when I look at it is with the inference scheduling path, that when you take a look at the backend pool, it's realized as decode being true and prefill being false. It's not that big a deal. The way I would like to say that is it's really the decode replicas in the chart structure, actually they're full service inference engines. They do both prefill and decode. So if you see that, don't be confused or lost by that. It kind of works, and we'll talk about that in just a second. The other thing I would like to point out is that the main innovation I see in this particular solution is, for one thing, it works, and it's multi-node ready, basically. But there's a lot of cool things that we can study and learn about and improve, okay? And this queue and load awareness that I just mentioned, Carlos mentioned prefix-aware caching, and how to do that very well, and then balancing. So these are kind of open areas, I think. And I'm a professor at the University of Washington. I teach high-performance scientific computing there. You have to take my class if you come through there, and I usually torture my students. And so you'll know that I like to see people take on those types of challenges and solve those problems themselves in different ways. So I took a look at this, and let's see what happened. Bottom line, the cluster I had access to is a TensorWave cluster. I have 16 nodes, MI300s. It's Broadcom backend, NIC. And when I pulled this, I realized, first of all, that the gateway is basically broken. It's got an old version, so I had to deal with the CRDs on this legacy setup that they had on that cluster and switch it to one that would be acceptable to the current stack. And so this is the kind of thing that you might see when you try to deploy some of these solutions. I'll go through some of the details here. So when you try to pull and deploy the manifest from upstream, I use this command right here, okay? And essentially I see that there's an error. It just tells me outrightly, ensure CRDs are installed first. Immediately, a lot of people are just blocked. So you go to your system administrator and say, can you help me with this? It should just be set up and working, right? You'll find that different versions can just trip up these software stacks. So we fix it, install the right version. It installs very beautifully. And you can see that on the right-hand side here. I'm not going to go through explaining all of the commands that I use, but basically you have to delete the CRD and then reinstall the correct one that's expected. Okay, and what else do I want to say? Another thing is that I'm going to just skip to this one. When I launched the manifest after getting the right CRD set up, what you found is on that cluster that other people are using it, and some of the nodes are busy. And then what happens is when the deployment occurs, it tries to launch pods onto nodes that actually have other people's jobs. And scoping that correctly and adjusting to that is kind of a nifty little thing. So I modified the actual manifest a little bit. This llm-d is rendered YAML, and I patched it with the ability to deal with some node affinity issues. With node affinity, you can basically use placement algorithms to try to look for busy state, or if you know a particular couple of nodes you want to target real quickly, you can just define them. And then I also use this topology spread constraints key here. And with that match labels, I can basically assign those roles. And if I find problems, I can just tell it, don't do it. Just don't schedule that node. So it works. And if I zoom in, after I launch that, it just kind of comes up nice and healthy. So this is what it looks like when you get it up and running, and you can start playing games with Inference. Let me go on. So you can then ask it questions, and you can look at this later, just posting chat to their chat and completions, and just watch it go through the system in Kubernetes on the back end, looking at the logs. Okay, so what I recommend is once you get this up, start playing with it. Look at the logs as you're doing Inference on the particular setup. I'm going to skip those because it's what I just said. And let's talk about PD disaggregation real quickly from the upstream. Okay, when I tried the upstream in this case, what I found is that we had a little bit of problem. I clean up first the cluster. Okay, so here are the commands I'm using. I basically define the namespace, get my Hugging Face token set up, make sure the namespace is there for me to use, and then I basically get started by trying to launch this Helm file command from upstream. And it actually does a pretty good job, except that it bumps into an error, which I'll define here in a moment and show you how we sidestep it. Explicitly recreate the service account. Okay, so what I did after I hit an error is I came in and I kind of modified the upstream YAML file and separated it into a couple of YAML files. And this way, I'm going to go in and try to debug what's happening. What I find, ultimately, when I take a look, I found that there's great progress actually in that upstream PR, and it works on the cluster that it was built on and tested on. But when I pull it to the TensorWave cluster that I'm using, it bumps into a problem. What's the problem? First of all, I say it looks pretty good in the sense that all these components of the cluster, of the deployment, come up. But when I take a close look at prefill and decode RDMA paths, they're broken. And I want that RDMA because we were talking about TCP. I'm looking for a higher performance standard for our work there. And so we're trying to get those RDMA paths and lanes lit up. And so what I found when I go in, I start a debug pod, and here's how I do that. I jump into one of those nodes, those pods, and then I take a look at the image, and I see that there's some missing RIXL or NIXL packages that have a mismatch in the paths and naming. That's a problem. And then the other thing is that even after forcing the IB devices and verbs libraries into that pod, the ECX path that's actually still being used doesn't actually come up on the desired RCIB path. So it basically just doesn't provide the right exposure, and the wrong lanes are taken. You get poor performance, but it still works. Okay. What I do to fix this, I'm not going to go into the great detail of walking through all this. I do want to say that you just need to have careful alignment with upstream VLLM ROCm images, which is what I want to talk about next. And the charts for these various NIC families have to be tested. Get those TLs and the RDMA paths and PD set up correctly requires making sure that those things are wired correctly, possibly before you push the image finally. So one of the things that I do or did here as an example is I did modify the Docker file slightly and built from a new upstream release of VLLM. And then I bake into that image benchmarks that allow me to test VRAM to VRAM, VRAM to DRAM, DRAM to VRAM, et cetera, on 1 and 2 node allocations from the cluster to make sure those lanes work correctly in the image. And then you can also try launching with Kubernetes in those just to get those tests run the same. And then I was able to render the upstream YAML. Okay, so if you want to see the kind of nonsense that I have to do to make those tests run, I'm giving you a litany of parameters here that you'll be able to see later, but if you look closely, there's a lot of library names here that you should know, but why is that doing that? Oh, sorry. Proving my inadequacy at PDF presentations. But basically, getting all these bind mounts and environment variables baked into your image is a bit tricky. Okay, so having a portable version of that, it might require, all I'm saying is it might require some alignment. Now, speaking of alignment, I'm just showing you how to run those tests on that image. And I'm not going to go through the commands, but you can set up the common environment variables on 1 and 2 terminals. On the same node, you can run the benchmarks, and then similarly, you can run the 2-node versions of these manually, just to make sure the image is working correctly, and check that those bind mounts are working correctly and that all the libraries are working so that you hit the right TLs. And we get a quick validation of the performance for read-write on 1 and 2 node, and I'm on my way. Even though I didn't show that for the performance element, but I will note that there's an interesting kink right there that's reproducible, and it happens each time, and this is something that we're looking at. Now, on llm-d YDP, I'm not going to talk about this more than to say that it's a work in progress. On the back side of llm-d, always you have an inference engine. For us, it's VLLM or SGLang. As I manage the VLLM team, I'm particularly interested in how it performs on our hardware. And so I'm going to take a look at what does happen here when we play some games with combinations of some of the other tools that we might consider as viable options for distributed inference. One of them is Mori. I don't know if you're familiar with Mori, but you can go read about it. And Rixel is our poor man's version of Nixel for from the ROCm stack. So after we reverse engineered it, we basically built Rixel. Now the question is, do we want to maintain that? And the idea might be that we partner up with NVIDIA's Nixel team, and they provide the global coverage for most of what we have to do. But for the time being, we have Rixel. Okay, and so I'm comparing Mori Rixel and the VLLM DPP Rixel solutions. Both of those are built on the UCX backend for the KB connector portions. And you can just take a look at the kind of performance we see on prefill and decode from Mori and DPP Rixel. And this is on an MI300 cluster, basically, with CX7 neg. Only thing I want to point out is that there's some noteworthy parts here. With VLLM, with DPP achieves 2K tokens per second prefill and decode performance. It's slower than the Mori solution considerably. And so it's something that we're looking at. And for distributed inference, we want to have these kind of measurements worked out so that we know what the best paths forward are. Similarly here, I'm looking again at EP-based solutions, and I'll let you guys dig through these solutions and numbers later. But one thing I find is that our V1 engine causes a lot of graph breakage, and that we see DPP has low latency performance issues. So we're debugging that currently. Oops. If I take a look and summarize what I really learned there, there are, looking at the prefill and decode side separately, we identified a handful of issues that we're trying to work on. Basically, the majority of time is spent in notification of the kernel, so these synchronization steps. And I'm going to let Tyler talk more about MOE because I think he's got a better talk prepared on it. But just to be clear, our Mori and DPP solutions with VLLM have been something we thought about pretty deeply before and then adjacent to the llm-d stack. I put this talk together last night, so let me read and make sure I'm not going to skip something. I think this comment right here, this out-of-the-box DPP solution currently only supports non-ADER MOE. I'm going to talk about that in just a second. And so it hits what's called the Triton version of the MOE kernel, which is 10 times slower. So the key here is getting lined up with our ROCm stack. And we're debugging that as well, by the way, that why is it that much slower? So what we do is take a look, and we see that if we take a look at the prefill, we identify that this whole step, this dispatch plus the ADER MOE step, with the combined takes roughly, in this point here, 2 milliseconds. If I look at the equivalent on the Triton backend, it's 255. And when we dig deeper, we find out that there's a gap there's a 9-second idle time between requests. So the debugging work that we're doing right now is really low level on our GPUs and trying to figure out how can we unlock that? How can we, first of all, identify the issue, and how can we unlock the performance that we know is there? Okay. I'm going to go onward. So those gaps are things we're trying to understand, and they tap into DBO, EPLB, and async scheduling that we're going to now talk about again. The other thing I want to talk about with our AMD effort and LLM-d is getting alignment with our upstream VLLM releases. And so VLLM has now a biweekly cadence to do their image releases. And that's pretty strenuous for us. We're currently on, let's say, 0.17. And ROCm, our VLLM stack at AMD, has also got images that we make, but there's usually a lag behind in our ROCm stack into what we're able to get put in that upstream release. And that jitter, that gap right there is something my team is working very hard to bring down. And in particular, we're also trying to capture important elements of these kernels that we need in our CI stack. And so there's active development in how to extend our current CI tests at AMD into the distributed regime where we haven't really defined and have very good tests there at this point. So for ROCm, if you're not familiar with it, it's this open source software platform. And essentially, if you go and dig into our ROCm stack, we're currently on 7.2. It contains, probably the most important thing is HIP, is what most people would know about. But we depend on quite a few of the libraries that get built in our ROCm stack into building our VLLM application. And so getting the right tools into that stack and aligning our upstream VLLM with that is going to be the core of delivering performance on the VLLM engine that gets bedded into LLM-d. So this is kind of something we're working on pretty hard. And I'm not going to expect you to look at this, but I give you something you can dig into later. These are the these are our GPUs. All I want to do is point out that in our GPU sets there, I'm only showing up, those are all of them except not the newest that's yet to come, but these MI300, 325, 350, 355 GPU stacks, just pointing out the differences in designs that we have to deal with VRAM on those GPU sets. So from 192 gigabytes to 288, and then a change in the number of compute units per die. That's interesting because it actually challenges us to have, to align the performance of our kernels that we put into our VLLM stack, okay? As for that, if you want to see what the dependencies that come out of ROCm that go into VLLM look like, go to our ROCm base in upstream VLLM, and you can take a look. It's really Triton, PyTorch, Flash Attention, Aider, and Mori right now. Those are the things that we're struggling and working hard all the time to get lined up with our hardware and get the highest performance on, and then get built into our VLLM image and get approved for a merger upstream. So this is kind of something my team's working on a lot. And as you can see here, we're also working on enabling MXFP4 MO weight type shifting and handling on our GFX 950 hardware platform, which if you know about it, has some support, native support for this data types, and I'm going to mention that briefly. Aider is, I'm not expecting you to look at this, but there's something, I put that here for you to look at later. These are a set of environment variables that you might need to get optimal performance on the ROCm stack when you run VLLM, and you want to bake these into those images you're building for LLM-d as well. So Aider is this AI tensor engine for ROCm, and it basically is tuned. Some of these are tuned in assembly, and the performance difference is 10x sometimes. Okay, and as it goes, model scoping in Aider for VLLM. Again, you have a handful of models here. And so MHA, MLA, Unified Attention, Triton Unified. So Triton Unified is basically the default. It doesn't use our best stuff, but it'll work. As you go further up, you can try for GPTOSS models and various DeepSeek models. You can try handfuls of these flags and just look at the difference of the performance you're going to get on those back-end engine servers. And then I want to point out all those flags. It's easy to get lost in this sea of environment variables. And in fact, I consider it a problem. It's not something I'm that pleased about. It's great to have knobs and things like that that you can set, but it is also very confusing to know what combinations to use on which models, on which hardware backends. And with that in mind, I would say that one of our head a VLLM maintainer and one of our head engineers basically makes this comment. For now, he advises to run on --fail on environ validation, meaning that combinations show up sometimes, as you can see up here. People run their codes and they use environment variables. There should be a V there. They use environment variables that we don't even have built into our stack upstream, and it just causes grief. I get so many emails a day about why doesn't this work. Okay. Lastly here, adjusting to these new data types that now have new native support on the hardware stack that we have impacts both model quantization and the scaling of these and their performance. So I'm giving you here a list of some of the nifty things. Let's just talk quickly about, let's say, MOE models. They have a disproportionate benefit coming from MXFP4 because the dominant gems in the expert FNNs are weight heavy, and so they tolerate low precision weight storage well. And this is exactly what we can do now to target that backend and to provide optimal gem kernels for that type of move. The others here are also benefiting from MXFP4, and let's just see how that gets built into our stack. In fact, there's a different type of data type defined here. Only our MX350 and 355 hardware has support for those new hardware data types in hardware. And right now we're actively trying to optimize our whole stack on it, if you want the truth. So if you want to cross-reference, you can come back here and take a look at that. Basically, the last thing there is our AMD Quark. Quark is AMD's model quantization toolkit. It has support for both MXFP4 and MXFP6, and also MXFP8, but really we're focused on the MXFP4 and on both its PyTorch, which is what we use for VLLM, and Onyx backends, and it's the layer that is used to quantize these models into MX formats. What happens is you get these weights in FP4, let's say, they come in, and then we have to cast them, upcast them, and do operations on them, and then we have to backcast them and things like this. We want to get everything working optimally on those 355 hardware, and then we have something else coming that's going to be somewhat interesting as well. So a lot of the MXFP4 work and dealing with those models is being teed up both in hardware and our efforts to get those built into our VLLM stack. I guess lastly, what I would say is that our work is definitely on VLLM primarily. We're interested and excited about llm-d. We're working on it. And yeah, I mean, I think that if you look at the main parallel modes in VLLM, it's TP, PP, it's data parallelism, expert parallelism, but getting those to be performant and current on our ROCm stack and on our new hardware that's coming, getting that alignment with those new features is a full-time job for sure. And that's what we're doing primarily. So hopefully we can continue to align the builds that we do for llm-d with our VLLM, our best performant VLLM engines, and get the lines correct so that you can actually get the right performance. So I guess I'll close with this. Why is distributed exciting and some basic challenges? Obviously, strong scaling. So if you can do inference faster, that's a good thing. If you have a bigger workload and you can spread it out and still keep pace, that's a good thing. Weak scaling is kind of trivial. We can add more. We can add more hardware and add more servers, for instance, and then the layer of scheduling becomes an important element. This balancing correctness and performance part, scheduling, is really an important problem, and I'm interested about the KV cache comments that were made, because things like speculation, prefix awareness, and so forth, how to balance that and get good performance, but still have that consistency. Because as soon as you go to distributed memory, maintaining a KV cache consistency is a deliberate act, right? It's not something you get for free locally. And so there's a lot of ways that we can talk about how to go about doing that. I think that we have more than realized the proof of concept of llm-d internally, even though we haven't published a lot of blogs about it. We're definitely still here, and I'm pleased to be here. And I would just like to add that in llm-d, for me, my goal would be to align with the open source software projects that we have at AMD, ROCm, and our upstream VLLM, and SGLang for that matter, so that we can get the best performance solutions into that stack. And yeah, I think that's important. Having that visual of targeting the right VLLM image that gives you that performance on the different pass-through llm-d is key to having a good performance on clusters that are made out of AMD GPUs. Okay, that's it.
Awesome. Thank you so much. And thank you again to AMD for being one of the sponsors tonight and helping us out do this event. Can't do it without their help, and that's what's really great here. So we've got 2 more talks. We're going to just keep the train rolling here. We'll probably skip Q&A towards the end because then we can go right to food. Speakers will all be here, so you'll be able just to chat with them out there. We've got some drinks. We've got some pizza and some salad and some other great stuff out there. So I'm not going to spend any more time up here. I'm just going to pass it off to Tyler for our next talk.
Nope. I did. Okay, there we go. Hi. Okay, so I am Tyler Smith, the chief architect of Inference engineering at Red Hat, and I'm a core maintainer of the LLM. I work on llm-d, and I lead the PD disaggregation SIG along with Rob Shaw. And then this is a presentation I was supposed to give with Nili, who unfortunately couldn't make it today. And I'm just going to be talking about YDP in llm-d and MVLLM. So this is one of our well-lit paths in llm-d, right? And it's really about taking this form of parallelization of multi-node MOE deployments of VLLM and incorporating them into llm-d in a nice Kubernetes way. So first of all, what is an MOE? So an MOE replaces a dense multi-layer perceptron with a sparse MOE layer. So like really the important piece here is this router. So this is a, it's a matrix multiplication that, decides what experts each token should be routed to. And really every large model that's coming out these days, and the vast majority of models overall are MOE models. Really like sparsity has won out here over really like dense models. And like here's an ablation study showing this done by DeepSeek. And so what they did is they kept the size of the model and the activated parameters constant. And they're showing that sparse MOEs really just perform better, especially even compared to just denser MOEs. So the kind of like trend we've seen in the past like year and a half is going from these like 7x8B kind of mixtural style models to these like DeepSeek style models where there are 256 experts and you select 8 of them. And so like here they're showing as you become sparser and also as you add these shared experts that you can kind of put the sort of state that every token has to think about kind of ends up in these shared experts. And then by making the experts more fine-grained, you can get more specialization out of them. And just empirically, the models perform better in this case. So this is like the style of model that we expect to see going forward, at least for now. And this changes a lot of things. So before this, we stuck to tensor parallelism. So you shard the inner dimension. We have one MOE implementation called fused MOE, really simple to implement and tune. And it doesn't, so that's all good. It doesn't scale well to multi-node, which is bad. And then expert imbalance, which I'll talk about in a bit, wasn't really a huge problem. But as we go to sparse MOEs, instead of TP, we have to do expert parallel and data parallel because the intermediate size becomes too small. It just doesn't make sense to shard that case. And then we also have to scale out to multi-node. One, to handle the memory footprint, to make size for the KV cache. But the nice thing is because of the sparsity of the router, of the MOE layer, we actually get to use sparse communication ops, so they scale better, which is really nice. And then like the high sparsity, it really wants high concurrency, and I'll talk about that in a bit. And then we do have to handle load and balance across experts. Yeah, and so, you know, key optimizations to handle this. Yeah, we're going from TP to DP. We're bringing in sparse all-to-all dispatch and combine ops. We have to deal with the expert imbalancing with something called expert parallel load balancing. And we also have to, because we're going to multi-node, we have to overcome the bottleneck of the communication costs that incurs there. So one key optimization we have is EPLB. So basically the expert routing is going to depend on the distribution of the tokens that we're seeing. And this is going to change between training and inference. During training, you can actually train the router to have good load balance across the different experts. But the token distribution changes with different workloads, and it changes from inference pre-training to inference. And so you're going to get a lot of load imbalance, and this is really hazardous to performance. So performance gets limited by the worker with the heaviest experts. So what we do is we replicate the heaviest used experts, and then online we rebalance them during inference. And so you can see here this sort of like balancedness of the experts without EPLB, and then with it, and then the red lines are, you know, the instance where we've done EPLB. Pretty heavy overhead. So right now we see about like 1/4 of a second is used during spent during EPLB rebalancing. We're working on that. Another key optimization, really important for H200s, is called dual batch overlap. So here you can see, this is from DeepSeek. This is a trace from the prefiller in a YDP deployment. And so what you do here is you break the forward pass into 2 micro batches, and that lets you do the compute from one micro batch while you're doing the communication from another. You can see here, like these are, this isn't like top is one batch and bottom is another. It's actually top is compute ops, and then the bottom is a communication ops. So top, you can see the linear operations are happening at the same time as these DPP combines, and the attention operations are happening kind of at the same time as these dispatches. Or actually, they're kind of all mixed up. Okay, so really important, you can get like a 2x on H200 by applying this. It's actually less important, we don't use it on GB200 because multi-node NVLink is 10 times faster than the InfiniBand or Rocky that you see on H200s. So I kind of want to talk here about like why we go wide. So I've got 2 slides. I'm asking here, how wide do we go? I mean, I'm not going to answer that, but it is like, we do have to go to multi-node, and the wider you get, the better throughput you can see up to some limit. So 1, KV cache size increases dramatically with scale. Here we're only going from 1 to 2 node, but if you see like the TP8 line here, this is particularly bad because on DeepSeek, because of MLA attention, if you use tensor parallelism, you end up replicating the KV cache. So just going to DP instead of TP gives you like a factor 8 there, which is really nice. And then going from 1 node to 2 node dramatically increases the size of the KV cache, just because like you're using almost all of the memory on the weights in this middle case. And so, yeah, KV cache really increases with scale, and it also increases, like, it's not like 1-to-1, right? So I will have more KV cache size per GPU at EP32 than at EP16. Okay, so important for long context, also important for concurrency. So here's some numbers we ran. Again, same H200 machines, where at EP32 and EP72, these were just the numbers I have from this run, showing the performance at 16 concurrent requests per GPU compared to 256 concurrent requests per GPU. So yeah, now we're getting into like a system at EP72 of thousands of concurrent, tens of thousands of concurrent requests to really like saturate compute in these MOE layers. And one thing to note here is actually at EP32, this workload barely fit at concurrency 256. And it's not quite saturated. So going big helps this case too. Okay. And then, so here's kind of like putting it all together. So we did a wide EP run on a CoreWeave H200 system with InfiniBand. So we show that we hit 2.2 tokens per second per H200 GPU running DeepSeek R1. And basically, we're saying like all of these optimizations we did a CLUML quant fusion, custom Cutlass kernels. We brought in some special quant kernels to handle the output layout of the DPP low latency dispatch combine. We did attention tuning for MLA, and we added EPLB and DBO in support of this. And like Red Hat drove a lot of this work. And so yeah, we can push up to like EP96 and drop performance a little bit. That would make sense for like a really long context runs. You get a lot of KV cache space in that case. And then overall we see prefill instances. You just stick to EP16, and if you need more prefill throughput, you just stamp out more prefillers. So for prefill, you just actually don't end up going that wide. In llm-d 0.5.1.5, we now support, so when we ran those numbers, we did not have support for this, but we now have experimental support for data parallel aware load balancing. So in this case, we can't get away from this issue that the entire node wants to live in a pod of Kubernetes. This is because of CUDA IPC enablement. Hopefully this might get better with DRAnet. But yeah, so in 0.5, we now have the ability to, we basically spin up multiple instances of VLLM. They're still combining together for EPDP communication. But then they each expose their own port, which then we can route to, so we can now do smart scheduling in the YDP case. And it's
Oh yeah, I got it. Thank you so
cool.
much, Nick.
Yeah, no worries.
Yeah. Did you send me the Slack invite also?
Somebody's mic is hot. Okay, we support PD as well. Okay, and then what's coming next? Okay, one, I deeply apologize for not having any GB200 numbers here. I tried real hard. We're having really bad numerical issues, but this is our current focus, is getting YDP running for NVFP4 for DeepSeek R1. Where we showed like a 2,200 tokens per second per GPU in the H200 case, mostly because we're switching to multi-node NVLink for the communication fabric. We can go to 10 at minimum, hopefully closer to 15K tokens per second per GPU on the GB200. We're also, as Kenny said, working on recipes in the upstream for YDP support on AMD GPUs. We're working on asynchronous and lower overhead EPLB. This is important. It's also very difficult because we hit a lot of hangs. We're also working on elastic and fault-tolerant EP, working closely with the Nixel team on these actually. So elastic EP, you want to be able to scale up, scale down within a deployment because the granularity is too large to auto scale at the granularity of deployments. And then fault-tolerant EP, like the scale of this, and also like the flakiness of GB200s, you know, occasionally. These things do crash, and ideally we can tolerate EP ranks failing without the entire server crashing. All right, that's it for me.
Just bring it back on time. All right. We're down to our last talk, and it's very late for our last speaker who was unable to get a flight from Israel. Nick is, here we go. Flip it over here. That's great. Do I unplug my laptop? Nope, you're just gonna do the thing. All right, Maroon, can you hear us all right?
Yep. Can you hear me?
All right. Well, I'm just gonna kick it right over to you. We've got our last speaker here, and then afterwards we'll filter out in the cafeteria. We've got some food and some drinks ready to go. But without further ado, Maroon, kick us off.
Okay, so I'll be speaking about KV cache in LMD, KV cache management. I'm Maroon, an LMD maintainer, one of the leads of SIG KV disaggregation. And I'll be kicking it off with a joke. So 2 LMs walk into a bar. The first orders a beer. The bartender goes, that'll be $3. The second says, same for me, but I'm paying cash. Now I can't hear you, but I assume everyone is laughing. This joke captures the essence of what we'll be talking about, and we'll dive into what KV cache is and what paying with cash means, and that effectively you're transforming your cache bills into cache hits. And that's the essence of efficient KV cache management. So kicking it off with what's out there in mainstream providers. So you see the cost problem. I'll start with a quote from the Manos, from one of the Manos blogs. Manos was recently acquired by Meta, which is a production level agent that was very popular and still is. So they say KV cache hit rate is the single most important metric for production. It directly affects both latency and cost. And we can see this also with mainstream AI providers, such as OpenAI, Claude, and others, where you pay 10 times less for cache tokens. And in this talk, we'll see how that is achieved in practice in production environments that run with LLM-D. So what is KV cache in short? So KV cache is a solution to make self-attention efficient. Self-attention is the step in which transformers understand context. You compute attention scores between every pair of tokens. And that operation, so since you're doing that for every pair of tokens, that operation is, it basically scales quadratically with context length. And it's the compute heavy step in a forward pass. That's the prefill step, which is what dominates your time to first token. And the solution is pretty much KV cache. So you save these calculations, you save the keys and values so that you're reusing them instead of recomputing them at every step. And we can see that nicely in I think this is a Hugging Face diagram or animation. On the top row, you see what you're calculating at every step. And what you're seeing is these repeated calculations are happening at every step. On the bottom row, you see in purple what you're pulling from the cache and what you're avoiding to recompute. So you're computing only the new information, you're computing only what's added. And VLM really did an amazing job at that. They kicked off with two key techniques. So today, VLM has a large set of optimizations that are essential for production inference. But if you look back at where they started, it was all about, and it still is, all about efficient KV cache management and efficient GPU memory management. So two key techniques there: paged attention, which is how they efficiently manage GPU memory for KV cache management, and automatic prefix caching, which allows for efficient and optimized reuse for these paged or for the KV blocks. In a simple example, over with 10K token prompts with Qwen 332B, you can see that the first request, so you're sending the same request twice. The first one takes 4.3 seconds. The second one is about 7 times faster. It's 0.6 seconds. And that's, so these KV cache hits or maximizing them is essential for good UX, for good TTFTs, and for optimized utilization of your compute. So we covered why KV cache is good for the attention phase, but it goes beyond just the single pass attention or the attention layers in forward pass. It works well with production workloads. So Prefix-Cache reuse in the wild. One mainstream pattern is multi-turn chat. You see that when in every turn you're adding more, a question or a query or whatever, but you're reusing the entire history you've built so far. So with every turn, you can reuse your entire history. And we also see the same with agentic workloads. So with linear agents, or maybe this is the one everyone is mostly familiar with. So with linear agents on multi-turn tool use, all the context is your history. At every step, you want to be reusing your history and not recalculating it again and again. And with agentic workloads, we see that, I think this was also mentioned in the Manus blog, the ratio of input to output can be 100 to 1. So Prefix-Cache reuse there can be super critical. And today in more advanced agentic patterns, on the left, you see tree of thought or parallel branching, where you have one shared prefix or shared context and parallel branching agents that reuse or have that shared context plus for a dedicated task or goal. And on the right, you also see a similar agentic pattern where it's this one is hierarchical swarm, where you have multiple children operating in parallel and one top-level orchestrator that gets the results once they're done. Also in here, there's a huge shared context between them, and orchestrating them intelligently can translate to a lot of cost optimization. So like Carlos and others mentioned so far, llm-d provides a set of valid paths that optimize for different things, specifically here on KV cache. So we have intelligent inference scheduling, we have KV cache management, and others that also benefit from KV cache orchestration. I'll be covering inference scheduling and KV cache management. So starting with intelligent inference scheduling, so we provide prefix cache awareness, we provide load awareness, and we combine the two to make optimal decisions to both utilize and orchestrate these prefix cache hits and also utilize the distributed hardware across the cluster. So llm-d provides some balancedness between the two to maximize performance and maximize hardware utilization. And just to give a simple idea of why you need intelligent scheduling, a simple example with standard load balancing, specifically here it's with Kubernetes. So when you get to production scale or production environments, you're not working with a single VLM instance that does all the KV cache management magic. you're working with multiple instances and multiple replicas that make it so that the unified KV cache becomes disaggregated. And if you're working with a naive load balancer that cares about distributing traffic evenly, what you'll be seeing is, so take an example, a user sends 2 requests at one turn or at step n. The scheduler decides that pod A should have the request. At the next step, pod B or any other pod that comes at some point in the turn gets the entire context, has to recompute everything, has to duplicate the GPU work. The user sees increased latency, and that KV cache you built up in pod A is now wasted. And in production environments, this is the default case. That's not just something that happens every now and then. That's pretty much the default case if you're not orchestrating requests intelligently. So we show some benchmarks for the intelligent inference scheduling path. So we provide different levels of prefix cache awareness, from approximation to precise affinity. And in an example workload that on paper demands only 73 of 16 H100 GPUs cluster, only 73% of the distributed KV cache. So on paper, you should be able to serve this workload very well. We see that in green and red, we have naive load balancing and load-aware only load balancing that shoot up in TTFT as the QPS or queries per second increases. While once you combine intelligent inference scheduling or precise prefix cache scheduling, you're achieving the theoretical maximum, which is intelligent orchestration and full utilization of the distributed KV cache. And that's what you get when you combine intelligent or prefix cache aware scheduling with load awareness, which we provide out of the box in the intelligent inference scheduling path. So we discussed efficient orchestration. That's all good and efficient, but you're limited by your GPU memory, which is maybe the most expensive resource in your cluster. Well, not maybe, I think that is the most expensive resource in your cluster. So in order to increase your KV cache pool, because at some point you're gonna hit a wall, you simply don't have enough KV cache to serve more requests. And to get over that wall, you either buy more accelerators or GPUs, or you increase your KV cache pool. So that's what we provide in the KV cache management paths. We have a north-south KV cache management path or set of capabilities, which increase the single instance KV cache pool with CPU offloading and storage offloading. So you'll be utilizing the readily available DRAM and file system or disk that you have. And on east-west management, we have KV cache sharing so that you compute once and reuse anywhere through an extended shared storage tier. So with these two, you both expand the distributed KV cache pool and you increase reuse through KV cache sharing. And on this end, so actually before we get there, just to showcase what this means for a large sustained workload, this graph shows 16,000 token requests being sent per user for a number of users on the horizontal axis, and the throughput you get on the vertical. And you see the first point on the top left is when your GPU cache is saturated, you're gonna start seeing evictions, and that's when performance drops. You see the first drop in performance. From there, CPU cache continues to sustain the workload, continues to provide KV cache hits until it's also full, and you start seeing evictions, you start chasing a tail, and performance also drops. Then comes storage, which is the largest tier, but it's not as efficient as with I/O bandwidth. It's not as efficient as GPU or CPU with loading KV cache state. But on the other hand, it's significantly bigger, and you can sustain performance for a much longer period and a much larger number of users. So this graph shows saturation growth and how offloading is essential to sustain a bigger workload or a bigger number of users with the same accelerator hardware. So I mentioned, or I discussed, KV cache offloading. Where are we doing that effort? That's pretty much all in VLM. At the moment, we have the KV offloading connector, which was contributed to VLM on top of the KV connector API. So the KV offloading connector exposes a simplified API that can allow for easily implementing offloading backends, such as CPU or DRAM or POSIX file system and any other memory tier in a much simpler manner than actually implementing the VLM KV connector API. So in there we have two offerings. One is VLM native. So with VLM out of the box, you get CPU offloading, a CPU offloading backend for the KV offloading connector, which is an asynchronous GPU to CPU offloading backend that utilizes DMA. And that's the first tier you saw on the graph. So you're offloading KV cache as your requests build up. And if your GPU has a miss, you look into the CPU tier and pull it if it's there. That's the first tier of your increased or your bigger KV cache pool. The second is storage offloading. We have this in llm-d. We have an file system connector that supports any POSIX backend out of the box. And that's the sustained tier you saw. That's the largest pool of KV cache, or increases the KV cache to sustain a higher or larger workloads. So that's it in llm-d. We recently released a blog on the file system connector. Give it a read and try it out. So here we have a simple experiment of 40 QPS workload, where we're sending a system prompt of 2,000 tokens, a short question, and a short answer. And we see that as the number of users grows, similarly to what we saw in the previous graph, storage offloading sustains the highest throughput. And I think at this point, you're convinced that offloading is essential for KV cache at production scale. So what's next? What are we working on? So in llm-d 06 and beyond, we'll be pushing, or we'll continue to push, the state-of-the-art in KV offloading. We have one roadmap in VLM that targets several optimizations, including HMA support, tiered prefix caching in VLM, and we have a wider roadmap in llm-d or llm-d KV cache that targets advanced storage offloading and advanced KV cache orchestration/scheduling. On the other hand, in the workload-aware domain, we're targeting agentic inference. So in there, we strongly believe that the next step in software optimization for inference will be workload awareness. And for the agentic workload, there's a lot of information to utilize and optimize on. Some of the work streams we're exploring are program-aware scheduler, where the scheduler is aware of the program level, so not independent requests, but tying different life cycles or different stages in an agent's life cycle to the same program. Context-aware eviction, in which we replace the naive LRU KV cache eviction policies with context-aware information. So you'd prefer to say keep a system prompt and evict some unique user question if you're able to. Or once your agent goes to a tool call, you know it will be coming back in a bit. So you try to keep the context so that it gets a hit once it gets back, and so on. Then there is semantic KV cache that adds these contexts that allow for implementing different eviction policies or different KV cache orchestration policies, such as duplicating KV cache in agentic swarms, and so on. And then lastly, there is proactive state management, where we proactively move state to, based on predictions, for example, to maximize KV cache hits before they happen. We have, this work is being run in llm-d in the agentic inference channel. Feel free to drop by. There is a lot of work. There's a lot of work for everyone pretty much in this domain, and contributions would be appreciated. So we do really invite you to join us. A lot of the contributions or core contributions in our work is community driven. You can find us on GitHub in the llm-d KV cache or the llm-d inference scheduler repositories, and on Slack in both the llm-d Slacks and the VLM Slack in the channels you see here. We strongly encourage you, and we really hope to see more contributions from the community. There's a lot of work to push, and we're very happy to work with the community. That's it.
All right. Let's give a big round of applause. I'm going to point the mic. You can only hear it if it comes through the mic. So hopefully you could hear the applause here. So there's a lot of ways to get involved in LLM-d, and that's going to leave you here with like a 1-minute slide just to show you the different ways. So, and there's really something for everyone. You know, there's a lot of projects in the AI space. You know, you don't need complex math skills for this. This is distributed infrastructure. If you're into distributed databases and networking and observability, if you like Grafana and building graphs, how do we monitor these things? There's so many ways to get involved in this project. You can check out the website, llm-d.ai. There's a ton of information on there. And if you don't find something, you can let me know in Slack, because I like to make sure that if you have a question, that means the website is incorrect. We are on GitHub LLM-d, the main project that is under LLM-d/LLM-d. Give that a star. People love stars. People love looking at star graphs. We want more stars. Give us stars. And also join us in Slack. As mentioned, all the conversations happening there. There's a lot going on. You can join the community calls. And actually, Carlos was wrong earlier. There's actually 8 special interest groups, because SIG-RL just started recently for reinforcement learning. I got that one right. So, so again, there's lots of ways to get involved. There's a lot of interesting stuff happening in the space. And honestly, thank you for being here, for showing up today, spending a couple hours to learn more about this. We've got some food. We've got some networking going on. Chat with everyone. And yeah, thank you very much. Round of applause for you as well for joining. We'll see you for the next one.